Welcome to the UW Synthetic Biology Online series. And this video is the second of two on bistability. In the last video I introduced bistability, and let me just review what we said there. So I had a gene network producing a transcription factor P, degrading P like so. The rate of production of P was V1, rate of degradation of P was some first order rate law like so. And I also had negative feedback. Let's just draw that. Something like this. Oops. Something like this. And P was suggested that P bound to some operator site upstream of the promoter, and that activated the production of P. So we had this positive feedback here. And this system showed bistability. So what I want to do in this video is do a simulation of this system to show it actually was bistable. So we'll need, in order to do a simulation, we'll need to set up some rate constants and some rate laws. This one we have already. This one needs a little bit of explanation. So let me just show you what that looks like. So let me just draw a graph. So if I plot V1 against P, it was something that looked like that. It was a sigmoid curve. Started at some basal rate. Let's call that B. Rose slowly, then more quickly, and then reach saturation. So what rate law might I use for that? Well, I could use a simple Hill equation. So it would look something like some V max, which is the saturation point, times P to the N, that's the Hill coefficient. Okay, divided by a constant plus again P to the N. And that'll give me this shape curve. The only other thing I have to add on is the basal rate. That gives me that displacement here. Okay, so using these two rate laws, I'm now going to build a computer model of this system. So let's go and look at the simulation application we're going to use. This is Jarnock. This is available for download on our website, sysbio.org. It's a scripting language and is specifically designed for modeling reaction networks such as gene networks. There are videos online that show you how to use this tool, but let me give you some hints here now. This section here defines the network itself. So if you look carefully, you'll see that describes the degradation of transcription factor P1 at a rate K1 times P1. This describes the synthesis of P, of transcription factor P1 at a rate given by that. You can see that that's the basal rate B, and that's the Hill equation there, with the Hill coefficients there and there. These terms here are just the sources and sinks. In this system, we always have to have a source and sink. These are not important here, but I still have to put them there. The sink, you can imagine, is the degradation pool of amino acids. The source here is the gene itself. In both cases, though, I put a dollar in front, which means these are fixed, so they don't enter into the dynamics of the model. Here, I initialize various values, for example, the Hill coefficient to 4. Here, I'm actually carrying out the simulation. This means from time 0 to time 4, generate 100 points, put those results into a matrix M. What this will do, it'll plot time on the first column and then whatever species we have in the model in subsequent columns. We only have one species, P1 here, so there will only be two columns, time and P1. I want to set up the axes. Let's set this up to something. Let me increase that so the y-axis is slightly higher. And then I'm going to plot M. So there's a command called graph. It takes as argument a matrix such as M. So let me run this and see what we get. Oh, there you go. Okay, so this plots then the concentration of P1 as a function of time. Okay, you can see it starts at 2, rises up to something like 9. Now I can change this, say if I increase the rate constant, what do you expect to happen to P1? Well, it starts at the same point again, of course, but now it drops back down. Okay, so how can I show that this system is bistable? Well, what would be nice is if I could plot a whole bunch of these graphs at different starting points and see where they end. If the system is bistable, I should be able to see, depending on the initial starting point, different endpoints. Okay, so remember that in a bistable system we had two stable points, and whether I end up in one of the stable points or the other depends on where I start. So let me go to this other scripting model I have here. This is the same as before. I don't need those two, but this time I've got a little bit more of an elaborate script here. So what I've got here is a loop, for loop. What it does, it iterates through a range of initial starting points for P1. So I've got a whole bunch of P1s in this list of numbers. The first thing I do is assign P1 to the first number from this list, then do the simulation. This will give me 2 columns. I then start a loop that runs through the entire R list, and each time it runs through the list it picks out a new initial condition, sets it to P1, then carries out a simulation again. Note that this is slightly different. Here I'm copying the results into M, but here I'm copying the results into MM. And also I'm specifying that I only want one column, and that's P1. So this just has one column which represents the concentration of P1, but it's at exactly the same time frame, 0 to 4, 0 to 4 with 100 points. What I then want to do is I want to augment the original M with MM, so I'm basically stacking up these P1 columns one after the other. I then switch off the display legend to make it look more readable, and then I plot M. Alright, so let me just comment these out for a second, and I want to because I want to show you. I want to make that run. So down here in the console, you can see it says OK, and I want to just show you what M looks like. So M is basically 100 rows. The first column is time, and all subsequent columns are P1 but at different starting points, and you can see here these are the different starting points. Okay, so I can now, let me go back to the script, let's bring that down, and then uncomment the display legend and uncomment the graph, and now let's run it. Here we go, and now you can see I've got about, I'm not sure how many plots I've got, but I've got a lot of plots. They all start at slightly different initial conditions. They aren't very different, but they're slightly different. The lower ones you can see evolve to the low state, and then there's a transition at some point where the higher ones transition to the upper state. So we have two states here, a low state and an upper state. If you see here near the middle, I have this point where it can't quite decide, or it takes a while to decide whether to go to the low state or the high state. And this point here basically represents the unstable state. So if I'm slightly below the unstable state, it'll transition to the low state. If I'm slightly above the unstable state, it transitions to the upper state. So this little simulation shows me that this system is bistable, and I can, depending on the starting point, I can either go to the low state or the high state. Okay, thanks.